The last portion is dealing with two theorems, the remainder theorem and the rational root theorem. The first theorem, the remainder theorem, says if we plug a k into your original function and my result is 0, then I know k is a 0 value. If it isn't 0, the result is my remainder. Now, that's pretty intuitive because if I've got a 0 value, so let's say x is equal to -5, and I know that's a 0 value, and I plug it in, shouldn't my end result be 0? And it should, because that is where it crosses the x-axis. So the end result is 0. So this remainder theorem is, the first part is telling you something you've known for years. The second part, though, if it isn't 0, the remainder that results is the remainder. That is the result of what we've just seen with synthetic division. Just a quick way in order to see, do I have a remainder, do I not have a remainder? And why is this important? This is important because we can quickly determine if we have a 0 value or a factor. You might say, well, synthetic division, that goes pretty quickly. Why do I need to know this other theorem? And let's say my polynomial that you are given, and this is going to be an extreme case, was x to the 99th plus 72x to the 54th plus 27x plus 9. Yeah, there's only 4 terms there, but remember with synthetic division, you need to have that 0 as a placeholder for every single decreasing power for your variable. So from 99 to 54, I would have to have some 45 zeros as placeholders that I'm doing synthetic division with. And then from 54 to 1, I'm going to have another 53 or 54 placeholders that I've got. So there's going to be a ton of placeholders, which doesn't really help us. But if I'm saying, okay, I've got x is equal to 1, I want to know, is that a 0 value? You'd plug 1 into the equation and see, do I have a 0 value being because the result's 0, or do I get something else, which then tells me I'm going to have a remainder. The second theorem, the rational root theorem, tells us all the possible rational roots. And rational roots is everything that can be written as a fraction or writing two numbers together. So it could be a fraction, it could be a decimal, which can be then converted into a fraction. It's really a ratio of 2 numbers, and that's where rational comes from. So we want to know, what are all the possible rational roots? All the possible integers, all the possible fractions that can come up from an equation. And this is usually the starting point when we're solving for polynomials. This does not take into account imaginary numbers. So determining all the possible rational roots of the polynomial, don't actually solve it out. The rational root theorem says if we take the factors of the front number and we put it over the factors of the back number, we will get all the possible rational roots. Actually, I take that back. It's the factors of the back over the factors of the front. Probably should write that correctly. Factors of the back over the factors of the front. And when you do factors over the back over factors of the front, you've got to make sure that your powers are in decreasing order. So here, 6x cubed plus 5x squared minus 10, we are in decreasing order, so it's factors of the back over the factors of the front. So I asked myself, what is the number in the back that I'm looking at? Well, it's a 10. The factors of the numbers in front are 6. So I want to list out all the factors of 10 and all the factors of 6. And I really don't care about the negative versus positive issue, because if I take 2 negatives, I'm going to get a positive, 2 positives are going to be negative, and I'm going to include that in my final answer. So I'm just worrying about what are the numbers. So the factors of 10 are 1, 2, 5, and 10, and the factors of 6 are 1, 2, 3, and 6. So the rational root theorem is going to tell me what are all the possible combinations that I can get for values. And all the possible combinations are the fractions I get. I can get 1 over 1, 1 over 2, 1 over 3, 1 over 6. Or I could have 2 over 1, 2 over 2, 2 over 3, 2 over 6. Or I could have 5 over 1, 5 over 2, 5 over 3, 5 over 6. Or 10 over 1, 10 over 2, 10 over 3, 10 over 6. Now, as I go through some of those are going to be repeated. Say, right here, this 10 over 5 is going to be the same thing as 5 over 1. They both reduce down to 5. So if I were to list out all the possible combinations here, I would have 1 over 1, which is 1, 1 over 2, 1 over 3, 1 over 6. And then I would have 2 over 1, 2 over 2, which we already have written as 1, 2 over 3, and then 2 over 6, which is the same thing as 1/3, so I'm not going to write that again. Then I've got 5 over 1, 5 over 2, 5 over 3, and 5 over 6. And then finally the tens, we've got 10 over 1, which is just 10. 10 over 2 is 5, I've already got that listed. 10 over 3, and then 10 over 6, which is 5/4, and I don't have that one listed, so or 5/3. So technically with that one I don't need 10/6 listed, because that's the same thing as 5/3. And then all these are plus and minus, so we just got to make sure we include plus or minus. So that rational root theorem tells me those are all my possible rational roots that I can get. I might have irrational roots, I might have imaginary roots, but the rational root theorem tells me those are all the rational possible answers that I can start with. And once I know those, that's going to be my starting point going forward to figure out, can I simplify or can I divide?